I'm going to talk through the solution to question 5 from the 2016 paper Numerical Methods for Partial Differential Equations. So in this question, you're presented with the one-dimensional advection diffusion equation. So here we have the equation, and said to find the variables v and alpha used here and describe in words the evolution of the solution. Okay, well v is an advection velocity, so if we ignore the alpha term for now, the alpha u xx term, we have the advection equation, and alpha is a diffusivity parameter. So if we ignore the vux term for now, we then have the diffusion equation, hence advection diffusion. Okay, so v denotes advection, alpha denotes diffusivity. What happens to the solution over time? Well, this advection term here means the initial profile moves along in the spatial direction, and this diffusion parameter here means that the initial conditions will diffuse or spread out. Okay, so it combines them both. Explain the process of term splitting. Term splitting splits up a PDE with multiple terms into several PDEs, each modeling a single sort of phenomenon. So, for example, advection diffusion equation, we can split this up into an advection equation and a separate diffusion equation. The advantages are maximum allowable time step for an unsplit scheme is a lot smaller than that of the individual schemes, so it allows us to use a larger time step, and individual schemes are easier to derive and implement than an unsplit scheme. Okay, so the next question is rewrite the advection diffusion equation as a system of two PDEs. And for each equation in the system, determine the differential operators. So if I just scroll back up to the unsplit equation, okay, so here's a single equation. I'm going to split this into two. And there we have the split equation. So this is the advection equation. This is diffusion equation. Now, differential operators, what we do is if we take the first equation, subtract v, first order derivative of u with respect to x from both sides, and I've written it in the form of differential operators. So little delta t of u means the first order derivative of u with respect to t. Okay, so this is simply subtracting that term from both sides. Then we've got to find the second order derivative, so find its derivative. Okay, well this delta tu, okay, is just going to be minus delta xu from the equation. Okay, so we put that in there. Of course, the order in which you've calculated derivatives doesn't matter, so I swap the order here. And then we've got another delta tu, so again, I take it from there, okay, put it in, and eventually we get this term. So this is a double derivative of u with respect to t, the advection equation. Do similar for the diffusion equation, and we get this. Part 2 of the question, use Taylor series to derive the following differential Marchant operators. So this LA, this means this is the Marchant operator for the advection equation, and this is the Marchant operator for the diffusion equation. Okay. So what we do here is we substitute in the Taylor series, the differential operators into the Taylor series. So we go one step forward in time, Taylor series, and I've done a second order one here. Okay, so we've got a third order error. Okay, so instead of u subscript t, I've written it in operator notation. Okay, well from the previous question, we can see that first order derivative of u is this. So I've replaced that there. Notice we've got the minus sign, and do the same the second order derivative with respect to t. Then if we factorise out the u term, so we've got 1u there, we've got minus v big delta t times little delta x there. Okay, so just simply factorise it out. That's the Marchant operator for the advection equation, and do similar for the diffusion equation. Again, Taylor series, replace the time derivatives with what you derived previously. Factorise out the U term, and you've got the differential marching operator for the diffusion term, or diffusion equation. Okay, part 3. Show that the operator sequence LD delta T and then LA delta T is equivalent to the unsplit marching operator. So I've given you the unsplit one here. Okay, and what this means is essentially we apply the advection operator first, and then we apply the diffusion operator. Well, to do that, because we're using operator notation, we simply multiply them together. So we have a fair bit of algebra to do here. We multiply these two, LA and LD together. Okay, we end up with some quite 4th, 5th and even 6th order derivatives here. Well, these derivatives are multiplied by, for example, this one is multiplied by delta t to the power 4. Now, since we're using an error, delta t to the power 3, this value of this error here is going to be larger than this one here. Okay, so we could ignore that one. And we could also do the same there. So that is the same order as that, so we can ignore that one. So anything, any derivatives, spatial derivatives of order 5 or more, we could just ignore. Well, we account for it in this error here. Okay, so do all that simplification, and we have this term, this line, which you'll notice is the same as what we were trying to prove, and therefore the split marching operator is exactly the same as the unsplit marching operator, provided we're working to second order. Okay, final part of this question, part D, suggest an operator sequence that can be used when the maximum allowable time step for one term is a lot less than the other. For example, let's say that our advection, the maximum allowable time step for the advection term was a lot less than that of the diffusion term. Well, in this case, what we can do is we can form multiple steps for the diffusion term using the time step for the advection term, and then just one time step for the diffusion term. Okay.